The last person that we are going to examine their contribution to the evolution of the atomic model is a physicist, very famous physicist as a matter of fact, named Niels Bohr. Bohr's contribution to our discussion centered around a problem that had confronted physicists for quite some time. And the situation they were examining and trying to develop an answer for was a situation where bodies, objects were warmed up and they were observed to emit energy. So energy was added in the form of heat, and then these objects then turned around and emitted their own energy. And the puzzling thing about this situation was that the energy that was released was not a continuum of energies. It was only certain values, only what we refer to as discrete values of energy were released. What we mean by discrete would be comparable to what you observed last year when you would compare, let's say, looking at white light and all of its components. If you looked at white light with a prism, you would see every color of the rainbow. It would be absolutely continuous. There would be no omissions in what you observed. On the other hand, if you looked at one of the lights, one of the colored lights that you used in some of your labs last year, let's say a red light, you would see that that red light actually was composed of different colors, and by no means would it include all of the colors of the rainbow, only certain colors. And that's what we mean by discrete. Only certain values were observed. And this puzzled physicists. They didn't have an explanation for what they are observing through experimentation. But Bohr came along, and at the time that he's tackling this problem, he realizes that atoms look something like what Rutherford had pictured, and that the problem was probably related, the answer was probably related to the structure of the atom that Rutherford had evolved. And in particular, he was convinced that it had something to do with the electrons in these atoms. And if you remember, Rutherford said that atoms had nuclei, that's where the positive charges were located, which we now know are protons, and also the neutrons would be found there. And all he said about the electrons is they were found outside of the nucleus. They were orbiting in some fashion, but he wasn't really very specific about it. But Bohr was convinced that the key to this warm body problem he was trying to solve had something to do with these orbiting electrons. So he developed a model, and his model he used to help explain what would happen to a hydrogen atom when it was hit with energy. So he pictured a hydrogen atom looking something like this. You have that central nucleus. Hydrogen atoms only have one proton in the nucleus. That's what makes this atom a hydrogen atom. We talked about isotopes before. Well, most hydrogen atoms are made up of the isotope that has no neutrons in the nucleus. And outside the nucleus would be a single electron. And you can see in the drawing here, this is how Bohr would have pictured the hydrogen atom looking like, that there was a single electron outside the nucleus, that in fact this electron would orbit around the nucleus at certain fixed distances. And in the picture I've drawn, this is depicting the hydrogen atom in what we call its ground state. And the ground state is when that electron got as close to the nucleus as it could. So you can see it's in the first ring. It can't get any closer to the nucleus. It's drawn there because, remember, protons are positive and electrons are negative, and you know about opposites attracting. So there it is, sitting the closest to the nucleus that it can. It's in its lowest energy state. This is called its ground state. It is very stable. That's where that electron wants to stay. Now, these concentric circles, really, in 3 dimensions, would be concentric spheres, can be referred to as either orbits, or some people refer to them as shells, and equally frequently they're called energy levels. So if I took a hydrogen atom and, like those warm bodies, I added energy to the atom, you'll do a lab later where we'll actually add electricity. We will hit hydrogen atoms with electricity. So the little squiggly lines up in the upper left-hand corner would be electrical energy bombarding this hydrogen atom. And once that hydrogen atom absorbs the energy, that electron isn't going to stay in the first ring, in the first orbit. It is going to move farther away because it's got extra energy. So it can overcome some of the attraction that the nucleus has for it. And it might jump up one ring or two or several rings. If we had too much energy, we could simply promote the electron right off of the atom, and it would be removed from the atom. But in this case, that's not what's happening. It simply got promoted, and these are some alternative places where it could end up. In this case, then, the hydrogen atom isn't in its ground state anymore. It's now in what we call the excited state, which is really unstable. That electron really wants to be back in that first shell. That's where it would be most stable. And that's where systems want to go. They always want to go to a stable state. But in order to do that, in order to drop back down, as I've depicted here using these purple arrows, we have sort of the same situation. Again, we can have that electron drop one shell or two shells or several shells. The farthest, obviously, it could drop is down to the first shell, the first orbit. And that's what it's going to want to do because it doesn't want to stay in that unstable excited state. But to do that, it's got to release some of that energy that it had absorbed previously when we hit it with electricity. And usually this energy is going to be in the form, very frequently, in the visible light spectrum. Maybe sometimes it'll be quite a little bit outside that. It'll be in the ultraviolet area of the electromagnetic spectrum. And if you remember from physics last year, that the energy of light is related to its color, to its frequency. So the farther that this electron falls, it might fall one level or two or three. The farther it falls, that would represent a greater loss of energy. So if I compare these three transitions, dropping one, two, or if it drops several, represented by the three there, when it dropped all the way down to the first level, E sub 3, energy, the third energy, that would be greater than if it dropped only two levels, and that would be greater than if it dropped only one level. So the farther that the electron moves, the more energy that gets released. And if you remember a bit about the energy, comparative energies of the different colors, you know that higher energies are associated with higher frequencies, so that would be sort of towards the violet end of the spectrum. Lower energies would start to move from the violet, and maybe E2 is around maybe the green area of the spectrum. And if it drops a short distance, which would represent less energy, the color is going to be somewhere towards the red end of the visible light spectrum. And so in this way, you can see how there's only certain energies that would get released because there are only certain orbits available. These electrons cannot orbit just at any old distance. There are certain fixed paths that are available for it to orbit in. So, once again, we have experimental evidence that isn't fully explained by the Rutherford model, so we, as always, we're going to modify our picture of the atom, and we have what we call the Bohr atom. And in the Bohr atom, you can see we still have that positive nucleus, because we're going to have protons and neutrons in there. And Bohr has developed a fourth model then. So he now specifies what's going on with the electrons that are no longer that aren't found in the nucleus. They're going to be outside there in one of these shells or one of these energy levels. And here you see it depicted different energy levels or orbits or shells that the electron could possibly reside in. The colors that we observed the hydrogen giving off, it's going to have a certain pattern. And hydrogen, you'll see in a later lab, there'll be a distinctive pattern of colors that are emitted. And so that array of colors, that pattern of colors, is what we call the emission spectrum. And every element has its own emission spectrum that is unique to that element. And so these emission spectra can be used to help identify what element is involved in a particular situation. This worked best, this model that Bohr developed seems to work best for explaining what we see with hydrogen. It was not as effective. It was not as good at predicting experimental results with other atoms. But you can see once more we've progressed a little bit further, that these electrons just aren't simply found outside of the nucleus, but are found in specific orbits, specific shells or energy levels. Bohr model, the fourth model, probably the model that most resembles what you have typically learned about the structure of atoms. So we've got the central nucleus with protons and neutrons found in it, and electrons orbit around that nucleus at certain fixed distances, certain shells, certain orbits. But this isn't entirely the end of the story. But this is what we would typically refer to as the classical model of the atom.